Hi everyone, and welcome to a Tech Talk video from Eric's Electronics Workbench. So over the years, many of these military-designed MEP-002A and the 003A diesel generator sets were sold off at auctions. Now these generator sets were manufactured in the 70s and 80s. This particular model was manufactured in 1982. And they're reliable generator sets, but if you ever find yourself needing to do troubleshooting on them, particularly on the AC voltage regulation system, you'll probably find that there's not a lot of helpful information that's out there. There are military tech manuals, but they kind of gloss over how the system actually functions. And there's a schematic conveniently printed right up on the top of the generator set on that control panel. But if you don't understand some of the functionality of the different components, interpreting that schematic can definitely be troublesome and confusing. So in this video, I'll clear up all of those mysteries and I'll explain exactly how the AC voltage regulation system works. And stick around because it definitely doesn't work in a standard way. It's not like a lot of other generator sets. And there are other military generator sets as well that were manufactured that don't use a regulation system anything like this model. So let's get started. I'll go ahead and open up the control panel and I'll point out the components that we'll take a look at on the schematic, and I'll show you on the side, they call it the reconnection box. It's where the main output terminals are at. I'll open up that side panel. There's some more components over there. We'll take a look at those real quick. And then just remembering where those components are and the names of them, when we look at the schematic, things will make a little bit more sense. So let's get started. All right, here we are looking inside the control panel. So this is the AC voltage adjust rheostat, which is marked as R1. This is transformer T2. This is a frequency transducer. It doesn't have anything to do with the voltage regulation. It just drives the front panel frequency meter. This is transformer T1, and that's assembly A2, and this is the voltage regulation circuit board. Now these two transformers provide voltage to that circuit board. Now there's more components that are related to the voltage regulation. They're down in the AC reconnection box, so let's take a look. All right, here's a view inside the AC reconnection box. Now the reason it's called the reconnection box is because this generator set uses a 12-wire generator. Technically it's a brushless AC alternator, but nonetheless 12-wire generators are very, very common design. But the 12 wires have to be configured or connected in such a way depending on the type of output you want from the generator set. So with this rotary switch up here, there's a knob on the front panel. This switch can be set to 3 different types of outputs, and this switch is only to be moved when the generator is not running, of course. So the main outputs can be 120 volts single phase, 120 240 volt single phase, or 120 208 volt three phase. And because this generator set does 3-phase output, that's why we see these 3 groups of wires down here. Now there's actually a high voltage range that can be configured on 12-wire generators, but this generator set doesn't allow for that. So on the back wall of this box, right back in there, there's a circuit board, a little bit hard to see, but back in that area, it's marked as A4. It's a bridge rectifier assembly, basically a 3-phase bridge, and it also has a resistor on that circuit board, which is part of the field flash circuit, and we'll see that on the schematic. But the bridge rectifier is part of the voltage regulation circuit. Now down in this corner, down there, you really can't see it, but on the bottom area of this box mounted in the corner is an inductor. It's marked as L1 on the schematic. It's actually 3 individual inductors. It's part of the voltage regulation circuit. And this large device here with these large loops of wires passing through these windows is actually 2 devices mounted back to back, all right? And this one says CT1 right here. It's embossed in the side. And that's a current transformer. So the purpose of this front section of this large device is to generate an output voltage on these terminals and these small wires up here that's in proportion to the current that's flowing through these large loops of wire. And it is used to drive the instrumentation on the front panel to show the load that's connected on the load meter. And it also is used to trip the circuit breaker if there's an overload. Now, something to keep in mind is on current transformers like this, you never ever want to allow a current to flow through these large wires with nothing connected to the secondaries. Because basically this is a transformer, this is the primary winding, this is a secondary winding. There's hundreds of turns of wire typically on current transformers on that secondary, and you will have a tremendously high voltage if you have no load connected to the secondary, and it's such a high voltage that it can often arc through the insulation and damage the transformer. So if you're ever troubleshooting one of these, never disconnect one of these and then have a current that's flowing through the large wires here that are looped through these windows. So CT1 has nothing to do with the actual voltage regulation of the generator set. It's only for the instrumentation and for the circuit breaker and protection. But on the back side, there's another device that looks similar to this front right here. It has the 3 windows. These wires are passing through it. It has terminals on the top with a number of different wires connected. And that is part of the voltage regulation circuit. And it's a very unusual device. It's marked as CVT1. In the tech manuals, it's referred to as a current voltage transformer. It's a little bit of an incorrect description. I've not actually seen such a device called that before, because you think, what is a current voltage transformer? Well, it's actually a magnetic amplifier. It's also known as a mag amp, and sometimes it's known as a saturable core reactor. And it's a very unusual device. You don't see them much anymore. Pretty much an old type of technology. And it's really key to how the voltage regulation works on this generator set. So let's go to the schematic and we'll take a look at all of these components. We'll see how they're connected. I'll explain how the whole system works. So let's check it out. All right, here's the schematic for the MEP-002A and the 003A generator sets. So the 002A is a 5 kilowatt with a 2-cylinder Onan diesel, and the 003A is a 10 kilowatt with a 4-cylinder Onan diesel. But the schematics are identical between the two generator sets. Really, the only difference was the number of glow plugs that were used on the engines. Now, MEP just stands for mobile electric power. So before I look at the voltage regulator circuitry, just a quick look at the main brushless alternator. So you can see the entire generator or alternator assembly is represented inside this dashed line. And this dashed line right here represents the rotating exciter. So everything inside this dashed line is rotating inside the generator. So this is the main field winding right here. So you have the DC voltage that's applied to this field from the regulator circuitry that we'll look at in a moment. And that causes a voltage to be created on this 3-phase rotating exciter right here. And this 3-phase voltage is rectified by these 6 diodes. Okay, so you have a bridge rectifier, 3-phase bridge. And that creates a DC voltage on this main rotating field right here. Okay, so this winding, this field winding is spinning or rotating inside this stator winding. So this is a stationary winding, which is on the basically outside frame of the generator. And you can see that the voltage that's then created in the stator is brought out on these 12 wires right here. And I mentioned it's a 12-wire generator. And those 12 wires are ultimately reconfigured in this switch over here, and then the main output terminals right there. So there's 4 main output terminals, and you use different terminals depending on how the generator is configured. 3-phase ends up using all 4 terminals, and for 120 volt single phase, only 2 of the terminals are used, so just different configurations. Main circuit breaker across right here, and you can see there's some more auxiliary contacts up here that are part of the circuit breaker, and up here and up here. Instrumentation, voltmeter, amp meter up here. This main switch across here is for selecting the different phases that you want to monitor the voltage and current on. So let's take a look at the voltage regulation circuitry. And the first thing that actually happens is when the engine is started, the alternator's field is flashed. And what does that mean? Well, you have to apply a DC voltage to the alternator's field to create the initial voltage, because if you just have the alternator spinning but do nothing else, there's not enough residual magnetism to create a voltage and to build things up and have the regulator take over. So to get that initial voltage, the term is to field flash, and that's done automatically when the engine is started, and as the engine is coming up to speed, the voltage is applied to the field. So this is part of the main control switch to start the engine up here. And this terminal right here has 24 volts on it. It's a 24 volt electrical system for the engine. So 24 volts is brought down here. There's a junction right here, and you can see there's a diode and a relay, and this is part of the engine control circuitry over here. But then you come down here, you have another diode right there. This diode prevents any voltage that's created later on by the voltage regulator from coming back into the electronics, for the engine. So the 24 volts is applied over here, goes all the way across, comes up this junction right here. We have a connection, but nothing happens over here. All right, if you follow this path across, we have a diode, another diode, another diode. This is the A4 bridge assembly that's in that reconnection box. But because you have a positive voltage, that positive voltage does not go through these diodes. All right, this is the negative or the cathode of those diodes, so they block that DC voltage. So the voltage comes up across here. If we follow this line over, it's coming up here, coming over here, all the way up through the field winding, okay, on the other side of the field winding now, we come over here, down, over to this side, come down here. Now we have a junction right here, all right? So what happens is, on this side of the junction, it comes over through this resistor R1 right here, up here, over on this wire, and if we follow this all the way over, this just goes back to the main ground terminal or the negative of the batteries. So that completes the circuit, and as long as the voltage is being applied off of this start switch, you'll have the voltage being applied over to the field, and it's flashing the generator and helping it to build up that initial voltage. So now let's look at how the voltage regulator actually begins to take over and control the voltage. So as long as the generator is producing a voltage, no matter how the AC reconnection switch is set up, there will always be about 120 volts on these two wires right here. And they come down to this terminal board here and here, which is in the control panel. And on one side, it comes over to that frequency converter and the frequency meter or the hertz meter right here. So that has nothing to do with the voltage regulation. But again, there's always 120 volts on those wires, or very close to that value. As the generator is starting up, of course, that voltage is rising up to that value. When the regulator takes over, it'll be very close to 120 volts. Now here's R1. That's the voltage adjust rheostat. So you can change the voltage up and down from that nominal 120 volts. So if we look over here, this wire comes up, it comes over here, and it goes to T2, all right? Here's the primary of T2, comes over, down, follows back over this way, and back over to the other line right here. So that's, again, 120 volts coming down to here, and 120 volts coming here. So we're just applying 120 volts to T2's primary. Now there's another transformer, T1, right here, all right? That's its primary. And if we look right here on these terminals, this just comes over here, comes through T1's primary, and comes back over to the terminal. And again, we had 120 volts across those two terminals, so we're applying 120 volts to this transformer. Now, if you look at this transformer here, the transformer is larger than this T2 transformer, okay? This is physically larger, it supplies a little bit more power. And there's a center tap on this transformer right here. And that center tap comes up here, and it goes over here into the terminal 12 on the regulator. If we look at terminal 12, move this over a little bit here, you can see what happens. This comes over, goes all the way up here. And you can see this is basically a ground connection across, or a common on many components that are in the regulator, but it's not ground as in the generator set ground. There is no ground connection, all right? It's important to know that. But it is a common circuit point within the regulator. And if we look at the secondary of this transformer, you can see right here the secondary winding comes off here and it comes over here, so we'll follow these two up. This comes over to here, goes across all the way up here, and it's applied to this diode, all right? And the other side right here comes all the way over here, it's up here, and it's applied to this diode right there. So these two diodes are just a full wave full wave rectifier, and you have a DC voltage produced at this point, and that DC voltage is then brought back out over here. So let me clear some of this off the screen. So we have a DC voltage that's coming out here now, and it's coming down this wire, it's coming out here, and it's on terminal 14. And we can see it comes across here, comes all the way up here, it's over here, and look where we're at. We are on the magnetic amplifier. So I'll talk more about how this functions, but for now, it's just important to note that it goes through this winding on the magnetic amplifier, through this winding, they're in series, through this winding, and out this terminal. Okay, so you can see it says C1 right there, and this is C2, which stands for control winding. And the voltage, if we follow this path down, it comes down here. On number 17 on the regulator, comes up here, and we're on the collector of Q3. If you look on the regulator, Q3 is a power transistor. So this transistor, how much it turns on is controlled by these two transistors over here. And this is basically acting like a variable resistor. So the path through this transistor comes back to that common ground point that I talked about. And guess what? That common ground point, remember, it goes back over here, comes back to this point, and back to that center tap on the transformer. So there's the complete path that the regulator is providing out to the magnetic amplifier. And it's important to note how that path functions and the test points that you might want to use if you suspect there's a problem in that part of the circuit. It's also really important to notice that this regulator over here, all of this circuitry over here, does not actually connect directly to the field windings up here. All right, there's a big misconception and misunderstanding that Q3 is somehow providing a direct connection into this field, and it's actually not. It's Q3 is only driving the control winding of the magnetic amplifier. All right, let's take a closer look at how the magnetic amplifier actually functions, because it's really key to the whole regulation system. So again, that's CVT1 on the schematic. So some of these windings we can ignore initially. So let's not look at this winding or this winding right now. Let's start with this winding right here. So one side of that winding comes over here, comes through inductor L1, comes over here, then comes up. And if we follow this wire all the way up, it actually comes up here, and it ultimately goes all the way over to this reconnection switch, and it's just being reconnected into another winding, or it's coming out of the stator ultimately. And if we look at the other side of this winding right here, it comes up, and you can see it makes a connection right here, and then goes over to the stator. And that's happening with this winding right here, and also with this winding right here. Each of those is ultimately being connected across a pair of the wires that are coming out of the stator. So these windings are just getting a constant voltage on them that's coming out of the generator. Now, we already looked at this control winding, and we saw that it has a DC voltage that's being applied to that control winding. So ignore that for now. Let's look at this other winding right here. So this winding, this one, and this one right here. So you can see they're actually all connected together, common on one side. This comes down, it comes over, it has a common right there, and then a common right there. And then the other side of the winding comes down, and it goes into the center of this three-phase bridge. And the same thing is happening here and right here. They're coming down to these common points on the bridge rectifier. Now, if you look at this as just a traditional transformer, you have a primary winding right here, and you have a secondary winding right here. If a voltage is applied to the primary, there's a certain turns ratio in the windings, and you'll have a certain voltage coming out on the secondary. All right, and that voltage is then rectified by this bridge rectifier setup down here. Now, imagine if you could alter the magnetism in this transformer. Well, that's exactly what a magnetic amplifier does, and it does that with this control winding. So if the control winding has no voltage on it, this will act like a traditional transformer, and you'll get the most voltage that can come out of here. So if you actually disconnect the regulator circuitry, or let's say that power transistor were to open up and not do anything, the voltage would go very high on the generator. So as this applies more and more voltage from the electronics in that power transistor and the regulator circuitry, as that drives more and more voltage onto this control winding, it basically saturates the transformer's core further and further, and it causes a lower and lower voltage to come out of the secondary. All right, so you're basically able to put a small signal into the transformer to control a much higher power that's being applied from the primary down to the secondary. So basically do have a form of an amplifier. That's exactly how a magnetic amplifier actually functions. It's changing or saturating the core of that transformer with this special control winding. So very ingenious design, very clever device that you really don't see much anymore. So this three-phase bridge rectifier down here, knowing that this is just varying the amount of voltage that comes out of this magnetic amplifier, we can see that this is the positive output right here, and it comes over here, comes up to here, comes over on this wire all the way up here. So we move this over a little bit here, comes all the way across, and we're up to the field winding. And we already saw that path when we followed it for the field flash. That was also the positive side. And then the negative output is right here, and you can see that comes over here, comes to this junction, comes all the way up here, follow that wire, comes up here. Ultimately it's coming across right here, and to the other side of the field winding. So there's a complete path right there. So the secondary of this magnetic amplifier is supplying AC voltage to this bridge rectifier down here, three-phase bridge, and the DC voltage off of this three-phase bridge is then being applied to the field. And the amount of voltage that comes out of the magnetic amplifier is controlled by this control winding, which is ultimately set and controlled by this power transistor right here. And that power transistor is driven by this pair of transistors right here. There's some additional sensing circuitry going on over here. And this voltage regulator is essentially looking at a constant reference voltage, and that reference voltage is set by the R1, the voltage adjust rheostat, okay, that has the set point. And if the main output of the generator set varies above or below that reference point, then this transistor is driven further or less, depending on which is needed, and that changes the main output voltage and brings it back in alignment with the reference voltage within this regulator. Now if we look over here, this wire right here has a junction and it comes down, and you can see that this comes back over here, and there's that center tap point, which is a common to a lot of this circuitry over in the regulator, and that has to do with some feedback that's being applied so that the regulator basically can see what's happening with the control over here. And this transformer right here is a part of the sensing network, so we know that it has 120 volts being applied on the primary, and the secondary is coming over here. It's ultimately going over here to this bridge rectifier, and you can see that that comes into some circuitry over here, which again has to do with the voltage sensing of the main generator's output voltage, and ultimately the reference voltage that's internal in here in the regulator. So let's go back up here. I'm going to clear off some of the markings on here, make this a little bit easier to follow again. So the final thing we should look at is this winding that we can see right here, and then there's another one right here, and then we can see that again right here we have one comes across right here, and again over here we see it repeated. And those windings are basically the wire that we saw looped through the current transformers and the magnetic amplifier, those large loops of heavy gauge wire. So you can see that actually, if we follow that wire up, that's just one of the outputs. It happens to be a T7 right there, and then the other side is just continuing on, and it goes over to the reconnection switch. Again, if we follow this wire up here, it's just coming over here from T1. So those are just main output wires. So as a heavier load is applied to the generator set, more current flows through those wires. It sets up a higher voltage that's induced in the transformer, and it's basically known as a current boost function. So it just helps out with the voltage regulation, and it just sets up a higher voltage within the magnetic amplifier, and basically is assisting with this primary winding right here. So the same thing is happening over here, and the same thing is happening over here. So again, these wires, these windings are basically, it's just a couple turns of wire that is this very heavy gauge wire that comes off the generator's stator. So if you enjoyed this Tech Talk video, please remember to give it a thumbs up. And if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. So as always, thank you for watching. And until next time, take care and goodbye for now.